Okay, we've already talked a little bit about Carnot maps. Sometimes we call these kmaps. And what we discovered in class was that you could use a kmap to help you apply some of the properties of Boolean algebra to simplify a logic expression. So at this point, we're going to get a little more formal with it and try to come up with a method for minimizing Boolean logic using kmaps. So to get started, we need to know, what does it mean to have the simplest algebraic expression? And the definition used in this book, and I think it's a common one, is one that has a minimum number of terms with the smallest number of literals in each term. Okay, so let's talk about what that means. A literal is a single variable within a term. It can be complemented or uncomplemented. All right, so let's take a term. Here's a term, A bar B C. It has 3 literals. If I add another term to that, B C bar, now I have 2 terms, and one has 3 literals, and this one has 2 literals. And if I add another plus, this would be, maybe A C bar. Okay, now I have 3 terms, with one of them having 3 literals and the other 2 having 2 literals. Okay, so let's give a few more examples. Let me scratch that. All right, so what if I had F is equal to A bar B or A B C as one expression, okay? And I had another expression where G, let's call it G, because I'm not making one up that's algebraically equivalent, but another expression where I had A bar B C D D. Which one is a simpler expression according to our rule? Well, in this first expression, we have 2 terms. Terms trump literals, okay? So in this expression for F, the first term has 2 literals. The second term has 3 literals. Okay, but down here in G, there's only 1 term. So 1 term is simpler than 2 terms, even though the 1 term has more literals. This has 4 literals. Okay, so what wins? Number of terms wins over literals. All right, but let's do another example. What if I had F is equal to A B bar or C D, and I had another function, A C bar or D E C bar. Okay, so I look at this and it looks like it's a tie on number of terms. Both F and G have 2 terms in them, and then so it comes down to number of literals. All right, so this has a total of 5 literals showing up, 3 in one term, 2 in the other. This one has a total of 4, and so F would be a simpler algebraic expression. Okay, so now you know what we're heading for. We're trying to get simple algebraic expressions, and if you read the book, there's more details supplied in the book. We're looking at minimizing sum of products. Sum of products. SOP. All right, so next, we've talked about literals. We talked about how we're trying to minimize things. The next thing we need to do is talk about some terminology so that we can come up with a method to describe how we're going to minimize a Carnot map. So the first terminology has to do with prime implicants. So I copied this straight from the book. A prime implicant is a product term obtained by combining the maximal possible number of adjacent squares in the map. Okay, so I pulled this out of your textbook, but there's some qualifying remarks here that are given in your textbook that you need to understand. Combining the maximum possible of adjacent squares, you have to work in groups of either 2 or 4 or 8 if you had a 16 variable map. If you had an even bigger map, you could go up to 16, but typically, we're going to look at group sizes of 2, 4, or 8. A group size of 3 adjacent squares don't combine. It doesn't work out. You need powers of 2 for the group size. All right, so you're looking for groupings. All right, and so a prime implicant is you take a map. All right, so let's make a map. All right, let's find the prime implicants. Okay, so I'm looking at this. I see a group size of 2 here. All right, it can't combine to a group of 4. All right, because there's not 4 ones that are adjacent. Okay, then I see another prime implicant here, a third prime implicant here. These can overlap, it's okay. And then we have this single one out here that's a prime implicant unto itself. All right, so this particular map had 4 prime implicants. Okay. All right. The next comment is prime implicants of a function. This is from your book. Prime implicants of a function can be obtained from the map by combining all possible maximum groupings of squares. All right, and so that's what we did here. We had 4 prime implicants for this map. All right, and then the next line that comes from your textbook is the simplified expression is obtained from the logical sum of all the essential prime implicants. Okay, an essential prime implicant is one that covers a 1 in the grouping that can't be covered in any other way. All right, so if you didn't include that prime implicant in the final description, you can't get the proper logic function. Okay, so back to the definition of how you simplify things. The simplified expression is obtained from the logical sum of essential prime implicants. You take all the essential ones, and then you add in whatever you need to in terms of other prime implicants so that you cover all the ones. All right, so the idea on this process is to identify prime implicants, second, use all essential prime implicants. So it's the min terms that can't be covered in any other way. And then use regular prime implicants, ones that aren't necessarily essential, or the ones that aren't essential. Use prime implicants to cover remaining min terms. All right, so this may feel fuzzy to you, so let's go through some examples. All right, so I'm trying to minimize this logic expression. Let's go with the simple 3 variable. Here's A, here's B, here's C, 0, 1. Okay, so there's our kernel map. So let's put this down as an example. Okay, and so we see here, we're trying to identify the prime implicants. Here's one. Here's another in yellow. Here's yet another in red. And here's yet another in blue. Okay, so which of the minterms are only covered by one of the prime implicants? So I take a look here. Minterm 1 is covered by both the green and the yellow. So, the yellow grouping is a prime implicant, not an essential prime implicant. Okay? Minterms 2 and 3 are covered by the blue grouping and the red grouping. I'm sorry. Minterm 2 is covered by the red grouping and the blue grouping. Okay? And then minterm 3 is covered by the yellow grouping and the red grouping. Okay, so minterm 3 is not covered by an essential prime implicant, but minterm 6 is. All right, there's only one way to cover 6, and that's with the blue essential prime implicant. So what we do here is we look at our groupings, all right, and we say, okay, we're going to need the green essential prime implicant, so we'll write that down, and we're going to need the blue prime implicant, so we'll write that down next. And then we will cover the rest in a way that covers the rest of the minterms. Okay, so let me erase the ones we're not going to use at first. All right, so let's write down what we get when we read the map for the green grouping. Okay, so for the green grouping, I'm looking at this. I span A, so A drops out. I'm outside of B, so I get B bar. Okay, and then I'm inside C. So that's the essential implicant, prime implicant, for minterm 5. Okay, and then I can also do the same thing with blue. I span A, I'm inside of B, and I'm outside of C. So I get BC bar. All right, now I just need to add one of the prime implicants that covers minterm 3. I need to remove all redundant prime implicants. Okay, so I have my choice. I could use this one, but I could have used a different one. I could have used grouped together minterms 1 and 3. All right, so I chose the orange one. Let's go with that. And so if I read that map, I'm outside of A, I'm inside of B, and I span C, so C drops out. Okay, so that's the orange case. All right, so going through this process, I have now minimized the expression for F. All right, so hopefully you see that. Let's do another. Let's make it a bigger Carnot map. Okay. So let's have 4 variables. So A is here, B is here, C is here, D is here. All right, so 0, 0, 0, 1, 1, 1, 1, 0. Label the minterms. Okay, just a reminder of what we're doing here. If I wanted 15, that's 1, 1, 1, 1. All right. If I wanted to know why, I'm labeling 6. 6 is 0, 1, 1, 0, which is the binary equivalent of 6. All right, so that's why we spent so much time working on binary representations. Okay, so we have this all labeled. Let me give you an example. All right, so we're going to do an example that looks like this. All right, and so I'm looking for the prime implicants. All right, so I'm thinking, you got to think about this minterm at a time. If I looked for a prime implicant to cover 1, the biggest grouping I can get to cover 1 is this one. All right. And then same thing with 6. The biggest grouping I can get for 6 is this one. The biggest one I can get for 12 is this one. So I'm essentially looking for stray ones. Okay, so those are not only the implicants, these are the essential prime implicants, because minterms 11, 12, 6, and 1 can be only covered with the implicants that are shown. But there's another prime implicant. It's this big group of 4. So we can find a different color. We'll go with yellow. This big group of 4 is also a prime implicant, but it's redundant because with the essential prime implicants, I've already covered all the ones. And so I would not include that in the minimized logic expression. Okay, so if I read this map, let's practice reading the map. All right, first let's read the blue region. Okay, I'm inside of A. I'm inside of B. I'm outside of C, so C bar, and I span D, so D drops out. Okay, so that's the blue part of the map. Okay, one color blue. All right, now let's read the orange part. Okay, I'm totally inside of A. I span B, so B drops out. Okay, I'm inside C and I'm inside D. So that's the orange part. Now let's go to the purple part. Okay, with the purple part, I've got outside of A, inside of B, inside of C, and it spans D, so D drops out. So we start noticing patterns here. If I have a group of 2, I have a 4 variable problem. When I group 2, 1 variable drops out. Okay, and we need the last term to finish off this problem, which would be outside of A, so A bar, and then I span B, so B drops out. I'm outside of C, and I'm inside of D. So that's the green region on the Carnot map. Okay, so I'm going to cut this off here so the video doesn't get too long, but I'll do some more examples on Carnot map minimization.